Welcome. In this video, we will consider some possible end behaviors for a function and learn how limits relate to those behaviors. End behavior for a function is the behavior that the function produces as x goes to positive or negative infinity. On the screen is a collection of a variety of different functions that exhibit different end behaviors. Take a moment and look at the different graphs. For each function, ask yourself, what is happening to the y value if we considered values of x so that x approaches infinity? And what happens if x approaches negative infinity? Please pause the video to write down your answers to these questions. For the first graph, which is the parabola y equals x squared, hold out your arms to match the shape of the graph. What are your arms doing? Both arms are raised high. This corresponds to y values approaching positive infinity. Both when x approaches positive infinity, x goes to the right, and when x approaches minus infinity, when x goes to the left. We write the limit of f of x as x approaches positive infinity equals positive infinity. This corresponds to the behavior on the right side of the graph. And we write the limit of f of x as x approaches negative infinity also equals positive infinity, corresponding to the behavior on the left of the graph. The technical meaning of these limit statements is that for any sequence xn with xn approaching positive infinity, so that corresponds to thinking of a sequence of x values steadily moving to the right. They don't have to be steadily, but they always need to be increasing without bound. If we look at the resulting sequence of the function, so at those x values, I ask what's happening to the y value. My y sequence is increasing without bound. No matter how high you set your threshold, the function is eventually always above that line. Let's now look at the second graph, which is the graph of a cubic polynomial. Imagine holding your arms out to match the shape of this graph as well. What does it look like? Can you see that your right arm is raised to match the graph, and your left arm is lowered to match the graph on the left? When x approaches positive infinity, our right hand, y approaches positive infinity, our right hand is up. When x approaches negative infinity, our left hand, our y is approaching negative infinity because it's pointing down. To describe this end behavior using limits, we write that the limit of f of x as x approaches infinity equals positive infinity. This corresponds to the right hand. And we write that the limit of f of x as x approaches negative infinity, that this limit equals negative infinity. This is our left hand because we're going to the left, and the value, the y value, is minus infinity because my hand was pointing down. We now turn our attention to the third graph, the graph of a hyperbola. So if I try to imagine what my arms look like if I were to mimic this graph, I might get hung up by trying to figure out how do I deal with this behavior where the graph breaks. This corresponds to a vertical asymptote at x equals 4 and is not actually part of end behavior. But just to clarify how vertical asymptotes relate, I'll talk about it very briefly. A vertical asymptote has to do with the limits as x approaches a particular value. So here we're interested in the limit of my function as x is approaching 4 from the right, and the limit of my function as x is approaching 4. I'm going to switch this because this is on the right hand side of my graph. I'll put plus there, and let's go back and change this to the left. All right, so on the right, if I'm looking at what's happening, as I pick x values getting closer and closer to 4, notice I'm moving to the left, but as I approach from the right, my y value is going up to positive infinity. Okay, that corresponds to the vertical asymptote at x equals 4. And if I approach on the left, if I pick values of x on the left, and those x values are getting closer and closer to 4 from the left, notice the y values of my graph are going down forever, and so I have a limit that f of x approaches negative infinity when x approaches 4 from the left. And so this is, these are the limits associated with a vertical asymptote. End behavior, on the other hand, is what happens as x continues to increase in magnitude away from 0, increasing towards plus or minus infinity. So I'll be looking at x values that are moving to the right forever. I imagine this graph moving to the right forever, and I say, what's happening to the y values in that case? And the end behavior on the left, I'm picking x values that are moving ever more and more to the left. And so this is the behavior that corresponds to my end behavior. I don't worry about the inside behavior, the middle. So what do we notice? On the right, my curve is steadily decreasing, but it's also flattening out. It's getting more and more level. Now, a graph can't show everything, so I don't know what's happening further to the right. For example, my graph might just sort of steadily go down, I can't tell, or maybe it actually levels out and becomes flat. A graph that's limited in its window, we just can't tell. But you know, this appears to be leveling out at a height of 1. So there's this horizontal line, y equals 1, that my graph is getting closer and closer to. This corresponds to a horizontal asymptote. Similarly, on the left, I can see that my graph is increasing in its, well, sorry, technically my graph is decreasing, because you always read left to right. But as I think about x values going towards negative infinity, the further left I go, the higher it climbs. And it's leveling out again. And it appears that I have this same horizontal asymptote. Okay, so both sides, I'm getting closer and closer to the value y equals 1. This is what we mean by limits at infinity. The limit of my function f of x, as x approaches positive infinity, this is moving to the right. My y value is getting closer and closer to a value of 1. And as I think about the limit of my function as x approaches negative infinity, as I go further and further to the left, the y value also seems to be getting closer and closer to 1. And these are the limits of my end behavior, and they correspond to the horizontal asymptote. Our fourth graph has oscillation. That is, on the left, we can see that my graph is going up and down, and this behavior that's repeating forever is called periodic behavior. The function just repeats itself. On the right, I also have oscillation. I'm going up and down, except this time it's not periodic because the size of my the amplitude of my oscillation is getting bigger and bigger. So if I want to think about the limits of my function, the end behavior, I want to ask myself, if I created a sequence of xn that's approaching positive infinity, so I'm picking x values, let me fix that. If I pick x values ever increasing, going towards positive infinity, and I ask myself, what are the y values doing? For these particular x values, I'm getting, that's already on its point, maybe there, this point's way down, this point here. there doesn't seem to be a necessary pattern of what's happening to the y values on this sequence. And so we say that the limit doesn't exist. If I look at the left, for example, if I pick my x values, let me make smaller points. If I were to pick my x values so that I was always picking the top of my graph, my y value would have a limit, let's see, this is a height of 5. My y value would have a limit of 5. If I picked my sequence instead to be always choosing the valleys, this time my limit would be -5. And a limit can't have multiple values. So if you can create different sequences that have different limits, we say that the limit doesn't exist. And so this oscillation is a classic example where we say the limit does not exist. So the limit of our function, as we're going to plus infinity, does not exist. And notice that's a sentence, not an equation. Limit of f of x doesn't equal does not exist. The limit of the function does not exist. And similarly, the limit on the left does not exist. The fifth graph that we consider also has oscillation, except this time my oscillation is tilted on a line. So I'm bouncing up and down, except I'm sort of steadily climbing as I go from left to right. So we want to ask ourselves, is there a limit this time? Well, if I think about x values, and I say what happens to my x value as I go further and further to the right, my graph might go up and then come down, but overall it keeps climbing. So what we do is we imagine considering an arbitrary high y value. So my high value is 15, but it could be 100. And I ask, well, what's going to happen as x approaches positive infinity? As I keep moving to the right, eventually I land above the line and never come down. Once I pass this value, which is somewhere around 18, once x is bigger than 18, I'm staying above this line. And this is going to be true for every line. No matter how high I raise my threshold, eventually I stay above it. This is what it means to say the limit of f of x is positive infinity. I go above any line I draw and stay above it. I don't drop back below. And so we say the limit of my function as x goes to positive infinity, because I eventually go above every positive line, I'm unbounded, my limit is plus infinity. Similarly, if I thought about big negative numbers, I'm eventually below it. And so this is what it means to say that the limit of my function as x approaches minus infinity is negative infinity. I'm unbounded in the negative direction. I go below every horizontal line. Our sixth and final graph also has oscillation. However, on this graph, the oscillation only seems to be large in amplitude in the center. So I've got large amplitude oscillations in the middle, and then my oscillation seems to be petering out. It's dissipating, or the amplitude is decreasing in magnitude. Now, just as with the horizontal asymptotes, a graph is never definitive. But it appears that the oscillation seems to be decreasing enough that it would go to 0. So if I thought about my amplitude seems to be vanishing, and if it does, if that amplitude goes to 0, the oscillation disappears, we would say that the limit approaches this horizontal asymptote. Now, an asymptote, you can cross an asymptote. The idea is I just start to become closer and closer. I stay close to that line. So we would say that the limit of this function, notice it's the same on both sides, the limit of my function as x approaches positive infinity equals the value of 3. because I'm getting closer and closer to that line. And the limit of my function as x approaches minus infinity is also equal to 3. In summary, we've looked at a collection of functions that exhibit different behavior. We've talked about functions that have limits of infinity, either like a parabola where both sides go to positive infinity, or a cubic where one side goes to minus infinity and the other side goes to positive infinity. We've talked about functions that have horizontal asymptotes, like a hyperbola where to the right and to the left we approach a y value, but also oscillations where the oscillation damps away so that we have a limit. We've also talked about functions that don't have limits because of oscillation or other reasons that the graph doesn't settle down to a value, nor does it keep going up or going down. And functions can have behavior where the oscillation might keep going, but as long as I go above or stay below a line, I might have an infinite limit. This is how we talk about end behavior in the language of limits.